written in this form. That small change in x times mass of electrons, small change in velocity greater than or equal to Planck's constant over 4 pi. What does it mean? According also to Heisenberg experiment, he found that the value of left-hand side equation might be greater than the value of right-hand side expression. Okay? So that's what you have to bear in mind. So then, if that the case, and that was the challenge has been discussed by the Heisenberg, now we like to draw the conclusion. What did he conclude? If he said that it's not possible to predict the position and velocity of electrons in an atom simultaneously, then what can we do as a chemists? Or what is happening? Or what the best he proposed, we say that in what the best suggestion. So he said that in the conclusion of what? Of Heisenberg is it's not possible to predict, to define means that to predict or to predict the position of an electron moving with the finite velocity. With the finite velocity. Finite velocity, yes, with definite velocity cannot be the definite velocity. So it's not possible to predict both the position of electrons moving with, or even just if you make this word of both, at the positions of an electron moving with the finite velocity. So then how can we do this? So that's the question. How can we determine, or how can we predict both position and the velocity of electron in the atom? Right? So the answer is, we say that it is only possible to predict the probability. It's only, not the exactly, it's only possible to predict the probability of what? The probability of an electron being at a given time okay, at a given time, and the probability is given at a given time, and this probability, the probability of predicting that is given by Schrödinger. Hey, say again, Schrödinger. So you have to make sure that Schrödinger. Okay? Schrödinger wave equation. So, because wave equation, because you like chemistry, in case you get your firstborn, call him or her Schrödinger equation. Yes. Why? Because you like chemistry. So you want him or her to have a unique name. Schrödinger. Say it again. Schrödinger question. So Schrödinger, this is another scientific Schrödinger wave equation. Schrödinger wave equations. The concept of Schrödinger wave equations is beyond the scope of this level. So Schrödinger wave equation. Say again, Schrödinger wave equation. So we say, unfortunately, the Schrödinger, okay, the Schrödinger wave equation is beyond this level, this A level is beyond. So you will cover the Schrödinger wave equations if you go to the undergraduate studies, then you'll find it. It means that you cannot understand if you teach you at this level. The Schrödinger wave equation, but what you have to bear in your mind, the Schrödinger wave equations is the equations which used to predict the probability of the positions and momentum or the velocity of of electrons in an atom, right? Okay, good. So that's the good news. So finally, say that the regions in the space around the nucleus where there is a maximum probability of finding an electron is called the atomic orbital. So now we have the word called the atomic orbital. Say with me, atomic orbital. Say it again, atomic orbital. Write in your mind, write in your subconscious mind, atomic orbital. So what is atomic orbital? Hence we've got the problem solving. What is atomic orbital? What's atomic orbital of what? Of atomic structure of an atom. Atomic structure of an atom. Right? So you say the atomic structure of an atom, we say that is the region. So this is the region. The atomic orbital is a region in space. In space, around what? Around the nucleus. Around the nucleus, whereby around the nucleus, where there is maximum probability. Maximum what? Probability. Maximum probability. Maximum probability. Okay, maximum probability of finding what? Electron. Maximum probability of finding electron. Yes, of finding electron in the finding an electron in the atom. So the regions where we have a maximum probability of finding an electrons in an atom, we call it in chemistry atomic orbital. Atomic orbital. Atomic orbital. right? So you have to make sure that you teach your kids about atomic orbital, right? Yeah, make sure that, because you like chemistry. I do like chemistry, so my kids, I don't know, but they will enjoy something like chemistry in my family, right? Okay, so that's how I used to transfer the knowledge with my physical, my analogy students. Okay, so if that's the case now, we are well now in the Heisenberg uncertainty principle. So let me take you to the questions now. I found 2 questions this lecture. You might find the other questions and I will solve it in another lecture. But I have 2 of the questions. So possibly I might solve one, and then I'll leave one for you to try it. Because that's how. So this will be example 07 in connections with balls. Okay, 07. And then these questions we say that the uncertainty in the momentum uncertainty in the momentum. Okay, in the momentum of a particle. Of a particle is 2.5. It's 2.5. That's for negative 14. Negative 14 gram centimeter gram centimeter per second. Okay, gram centimeter per second. Find its approximate position. Approximate position of what? Of this electron. Approximate position of 40 of electron. So given Planck's constant is equal to 6.63 exponent negative 34 joule second. And pi is equal to 3.144. For all the people or all the students who will be doing this question to get the same response. Okay? So solution. So let us read the question first. The uncertainty in the momentum of a particle means that what is that particle? It's an electron. I will teach you the other atomic theory, that is wave duality, which has been introduced by Louis Victor de Broglie, okay? The French mathematician, the French physicist also. So when I'll be teaching you, we'll find another concepts or another belief or another truth concerning about what an electron is a wave particle, and also an electron is we call it it's a wave in nature, and also it is particle in nature. So it has both properties, that means of the wave particle or wave duality nature. Wave particle duality nature. So the uncertainty of the momentum of electrons of a particle is 2.5 exponent negative 14 grams centimeter per second. Find its approximate positions of an electrons given that one. So, but the questions didn't tell you that whether use the Heisenberg or use the Bohr's atomic or use the Planck's constant or use the Riemann equations. The question didn't define. But because I taught you, this is simple, just like taking a chocolate, isn't it? Yeah. So let us realize if it is real simple or it's not simple. But there is a trick there, which after that you have to concentrate in order to identify it. It's directed, but the trick is there. Okay. So the first step, okay, we have been given some data. So let us maybe say data given. Okay, we've been given some data. We have Planck's constant 6.63. This is exponent negative 34 joules second. And also we've been given the speed of the light. We don't need the speed of light. Pi. Pi is equal to 3.14, right? And then so what will be given is momentum of what? Of the particle, which is electron. So this is change in momentum, change delta P. So this is delta P, 2.5 exponent what? Negative 14. But the unity is grams centimeter per second. That is the unit which has been given there. So what is required is the approximate position. So approximate position, this means that delta x is required. So this is what is required. Okay? So we go for the second step. Second step, in order to deal with this problem, we have to recall the mathematical formula, or recall the mathematical formula of whom? Of Heisenberg. Heisenberg uncertainty principle, right? Uncertainty principle. How does that formula state? It states that the product of changing positions with the change in momentum, this will be equal to Planck's constant over 4 pi. So the questions asked here determine the change in positions. You have to make the subject is Planck's constant, then this is 4 pi, this is delta momentum. So then this is delta x. So delta x is equal to Planck's constant, right? Which is 6.63 exponent what? So negative 4 joules second, okay? Joules seconds, and then what we say that this is 4 pi. So delta, this is 2.5 exponent 30, so negative what? Negative 4. But again, we have something very important we have to take care of. Before we do this computation, okay, we have now the formula, but we have to take something into account before we proceed. Okay, this is the formula that we're going to use it, but we have to do something in advance. And this is the steady step. The steady step, we say that let us express what? Express the momentum in its SI unit in kilogram meter per second. Because we've been given its quantity in gram centimeter per second. So then we have to do the unit conversion process. That's one of the trick there. So I would like to remind you, remember that 1 kilogram is equal to 1,000 grams. So it means that 1 gram is equal to 1 exponent negative 3 kilogram, right? And then remember that 1 meter is equal to 100 centimeter. So then 1 centimeter, this is equal to 1 exponent negative 2 meter, right? So if that's the case, so in case that we have a product of 1 gram, there's 1 centimeter, this will make it 1 exponent negative 3 kilogram multiplied by 1 times 30 exponent negative 2 meter. So it means that 1 gram centimeter, 1 gram times 1 gram centimeter, it will be equal to 1 exponent negative what? Negative 5 kilogram meter. Right? So if that the case now, in case that, so it means that the 1 gram centimeter per second will be 1 exponent negative 5 kilogram meter per second. What will be given there? 2.5. So it will be given 2.5 exponent negative 14 gram centimeter per second. This is equal to how much? So this is x, or this is delta, the momentum now. Fantastic. Enjoy the beauty of SI unit, the beauty of 40 measurement. This is all about measure. If you didn't understand, you crammed it during your 4 months, now you have to suffer. That's the truth. Because we missed this problem. We missed this question. So we say that we have delta momentum. The unit is gram. Remember that gram, centimeter, second, and second will cancel. So simply say that it will be 2.5 times 10 exponent negative 14 times 1 exponent negative 5. But now the unit is gram meter per second. So then we say that changing momentum is equal to what? Changing momentum is equal to 2.5 exponent negative, add the exponent. The base are the same as 10, then add the exponent. Because if you multiply exponents to the same base, we add the exponent, or we add the indices. So the indices there will be negative 19 kilogram meter per second. So this now, it's a new momentum. We can even call it delta P2. Right? So this was our first momentum, which is delta P1. Okay? So then now we have a momentum, we can determine what the position. So determine the position now, so this we say that you have to go to the first step. So the first step, we say that now let us compute the position, the estimate position, delta x. So if you compute the estimate position, which is delta x, okay, so if you compute that one, so you say that delta x is equal to what? Is equal to Planck's constant over 4 pi delta P2. So this will make delta x is equal to Planck's constant, which is 6.663 exponent negative 34 joules second. And then this is 4 times pi, which will be given 3.14. Don't use the one that in the scientific calculator. Times 2.5 exponent negative what? Exponent negative 19. But the unit is what? The unity is kilogram meter per second. So you have defined joules. Something will cancel there. You have per seconds. Then it will be second square. So we have delta x. So you have to use the scientific calculator in this simple division. However, that you can just simplify some of the items there, that this is exponent negative 34. You add, remember that if this will become the numerator, so you add with 19, it remains with what? Negative what? Negative 15. I'm not mistaken. Yeah, negative 15. So then you divide, you multiply, you use your scientific calculator effectively. Then the estimation, so the approximate position is 2.11 exponent negative 16 meter. Okay, so it is 2.11 exponent negative 16 meter. It's the smallest positions, and this is the position from the positions where we find electrons to the nucleus of an atom. Right? So that's why it is very small. And that's why you see even the size of electrons, protons, and the neutrons are very small. You see the way that the distance of electrons to the distance from the positions, or from the point where the electrons is formed to the nucleus, is 2.11 exponent negative 16 meter. It is 0.000000000000000. The zero, the point, it should have 16 decimal places. It means the all 0 zeros and then 2, 1, 1. So then we say that the approximate position now, therefore, the approximate position 40 of electron. So approximate position of the electrons in the atom is what? Is 2 into 1 exponent negative 16 meter. So this is the response. Okay, good. If you have any questions, you need to understand any point, because our intention in this channel to make students understand the general chemistry or the advanced chemistry. So if you didn't understand anywhere or any point, please ask in the comment section. If you have any extra questions concerning about the concept, you can ask us in the comment section. So now we have example 8 of Heisenberg uncertainty principle. But this one now, I want to leave it as homework, what? Homework 9. I left my homework in lecture 8. I don't know if you've done it. If you did, please let me know. What is minimum? What is minimum? So what is minimum uncertainty? Uncertainty, or the minimum uncertainty in position. In position as imposed by the uncertainty principle. By the uncertainty principle. On 100 gram ball thrown at 42 plus or minus 1 meter per second. So this is the question. What is the minimum uncertainty in position as imposed by a certain principle on 100 gram ball thrown at 42 plus or minus 1 meter per second? Hint: you have to understand the concepts of error. Plus or minus of meter, plus or minus meter per second means this is maximum. This is maximum what? Maximum error. Maximum error in velocity, maximum error in measurement of the speed. Maximum error in measurement of what? Of speed. Okay, measurement of speed of the ball. Measurement of speed of the ball is 1 meter, is 1 meter per second. So that's maximum error. So hint: plus or minus 1 meter per second square means the maximum error in measurements of speed of the ball is what? Is 1 meter per second. So make sure that you do that homework 9, homework 09. Okay, homework 09. We had in lecture 8, I gave you homework 08A, homework 08B. So this is only, so this is the homework 09. Okay? It's simple question. For my students, this is very simple questions. I don't know about somebody's students, but for my students, this is the simple question. If you join me from the beginnings to this, from the beginnings of this lecture to this point, this is a very simple question. Believe me, that's the truth that I'm telling you. Then, okay, so then let us go to another concept which is very important for this concepts of atomic theories. And then when we take that concept and then we'll go and having something which is a little bit different. So the concept is, which I have to carry on, this is called the concept of wave. But okay, I think that this is the end of this session 09. I would like just to start another session. So join me in the session 10, where I will be teaching you about the wave duality nature of electrons, so that you'll enjoy the whole concept. So I would like to thank God that for this moment that He has given me, and the power and the energy and the wisdoms to teach you. And I would like to thank you also, take some of your time to watch this video from beginning to the end. I really appreciate what you have decided and what you have gained. I would like just to remind that to make sure that you subscribe, and then you share these contents to your colleagues or to your friends, so that many students may be assisted concerning about the concepts of 40, the concept of Heisenberg uncertainty. This is not the end of Heisenberg uncertainty principle. You can spend much time on going through the principle of chemistry books, or reading some chemistry books, going online and dig in details about Heisenberg uncertainty principle. Very lot, but I've tried to squeeze and even just to take the requirements of the syllabus of advanced chemistry for advanced secondary schools in United Republic of Tanzania. So thank you very much. May God bless you. See you in the next lecture.